So once again, good afternoon. Compactness we have discussed in the last lecture. Let us revise the definition of compactness. So let X be a topological space, a collection UI of open subsets of X. Is that collection is called open cover of X if X can be written as a union of UI. So cover means the collection of sets UI, its union is X. But open cover means each sets in this collection is open. So each UI is open. That means it is a collection of open sets, and which covers X means its union is X. So this is meaning of open cover. And if every such open cover contains a finite subcollection which anyway will be open subsets because it is a subcollection of this collection, and if union of those finitely many open sets is X, then that subcollection is known as finite subcover. So that is basically the definition of topological space. If given topological space X is compact, if I can write X as a union of UI, I belongs to I, where UI is a element of tau x, then whenever such collection is given arbitrary correction, we can always find a sub collection which contains finitely many open sets, and it will cover entire X. So union of UIs will be entire X, and those UIs will be finitely many. So this is meaning of open subcover. And then we have seen that the real line is not compact because if we cover the real line by this particular collection of open sets, then for this particular collection of open sets we cannot find finite sub collection which covers R, because finite subcover will be bounded set and R is unbounded. On the other hand, we have seen a subset of R. So what is meaning of a subset is compact, we will discuss in today lecture also in more details. But why this particular subset is actually compact set? Because if I take any collection of open subsets which covers this particular set, then in fact I can choose a finitely many sets which cover this set, and they are open. So therefore this is a compact space. So what is the exact definition of a subspace is compact is given here, that if Y is any subset of topological space X, so on which since Y is a subset of X, we can define the subspace topology on Y, and that is defined as a set is open in the subspace topology on Y, which is a subset of Y. It is open if it is intersection of an open subset of X with Y. So that is basically the subspace topology on Y. Then a collection of subsets of X is which covers Y means Y is a subset of union alpha A alpha. So in the definition of the topological space X is compact, we are taking X is equal to union of UI. But when we consider this the subspace, we take Y is a subset of union AI, not equal to, right? So this condition is different here for the subspace case. So therefore we define cover once again for the subspace, and this is a small lemma that if Y is a subspace of a topological space X, then what is the criteria for becoming Y is compact with respect to the subspace topology? So this result will give us the condition that Y is compact with respect to the subspace topology if and only if every open cover, so these are the A alphas are the open set with respect to the A alphas are open set subsets of R. So A alphas are open with respect to the topology on X and it covers Y. That means Y is a subset of union A alpha. Then this particular cover A alpha has a finite subcover. So once again, what is a subcover? Subcover means we have to choose a finite sub collection of given collection, and it unions covers the entire space Y. It union covers the subspace Y. So let us start with the condition that Y is compact, and we will verify this property. So suppose Y is compact subspace of X. That means if Y is has a open cover, then opens Y is a open cover which contains the open subsets of Y. Then it has a finite subcover. So that is meaning of Y is compact. Y is compact subspace. So now what we want to show is we start with a collection A alpha of open subsets of X which covers Y, and then we will show A alpha as a finite subcover. So let us start with A alpha, which is a collection of all open subsets of X. So A alpha is open with respect to topology on X now, and it covers Y. Means by the definition Y is a subset of union A alpha. Alpha belongs to I. I is some index set. So since Y is a subset of union A alpha, we know that every set is its intersection with itself is the same set. So Y we can write as Y intersection Y, and then one of the Y we can replace with this condition that Y is a subset of A alpha. So that we will substitute here in the first place. So what we'll get is this is a subset of this. Y intersection Y is a subset of union of A alpha intersection Y. So we have used here distributivity, that union is distributive over intersection. And once we get this set, we can denote by B alpha. So basically Y is a subset of union B alpha, where B alpha is A alpha intersection Y. So since A alpha is open set in X, A alpha intersection Y is open in the subspace topology on Y. So this belongs to tau Y now, and basically Y has an open cover of subsets which are open in Y, and we know that Y is compact space. So every open cover has a finite subcover. So basically we got a cover of Y which is B alpha, and B alpha is open in the subspace topology on Y, and since Y is compact in the subspace topology, that is the hypothesis. So this cover has a finite subcover B alpha 1, B alpha 2, B alpha n say. So this is a particular subcover which is we are getting, and therefore so this is a finite subcover means what? Finite subcover means this condition. Y is a subset of union B alpha j. J is running from 1 to n. And then we know that B alpha j is alpha j intersection Y. So what we got is Y is a subset of this union, and once Y is a subset of this union, Y is a subset of union A alpha j. Alright, because If I have X, I have Y, and suppose Y is covered by, let us say, A1 and A2, then that means that if Y is covered by A1 intersection Y and A2 intersection Y, then you can say that Y is a Y. So Y is a subset of A1 intersection Y, and Y is a A1 intersection Y union A2 intersection Y. Then we can say that Y is a subset of A1 union A2, right? So this thing we are using here. So from this we can write this one, and so these are the just basic property of set theory. So what we got is we got Y is a subset of Y is covered by a finite subcover, right? Y is a finite subcover. So we started with cover A alpha, which was an arbitrary cover of Y, and then we proved that this cover A alpha is a finite subcover. So that is basically this property we have verified. So by assuming Y is compact, we proved this property. Now conversely, we will assume this property and we will prove that Y is compact. So to show Y is compact, again we have to start with cover, and then we have to prove it has a finite subcover. So let us consider that C alpha. So this cover, instead of alpha, I will denote alpha dash, index by alpha dash. We can also use some other index like beta, gamma, but I'm using alpha dash. So let's see alpha dash be covering of Y, where C alpha dash is open in Y. So we want to show that this cover has a finite subcover, right? That is what we want to prove, that Y is compact. That means any arbitrary cover has a open cover has a finite subcover. So the C alpha dash is a open subcover of Y. Open cover of Y, and C alpha dash is open in Y. That means what? Each C alpha dash is of the form A alpha dash intersection Y, A dash alpha dash intersection Y, where A dash alpha dash is element of tau X. So here I am using A dash because we already used A alpha earlier. So to not get confused, I am using A dash alpha dash. But this dash does not have any relation with the complement of the set. It is just some set. So in otherwise we can also take B alpha dash, right? But just for different notation, I am using A alpha dash, A dash alpha dash. So alpha dash is uh, other than alpha, and A dash is other than A. So that is the only notation we're using here. So what we were discussing is that C alpha dash is open set in the subspace topology. That means it is a of the form some set intersection Y, where that set is open in X. So this is that set which is open in X, and then we know that Y is subset of C alpha dash, and C alpha dash is this set, so that we have substituted here, and then we can again use distributivity for union and intersection, so we will get this thing. And once again, if Y is contained in that union alpha dash intersection Y, then from this I will get Y is a subset of union alpha dash A dash alpha dash, where this particular set is open in X. So now we have a open cover of Y by the sets open in X. So I can use the hypothesis. We are proving the converse part. So that hypothesis of the converse part we can use, and that will give a finite subcover of Y, which the sets are open in X. So this open cover has a finite subcover which has say, let us say m elements, and all the sets are open in tau x. And once I will get this thing, then we know that the relation of C alphas and A alphas. So we know that C alpha dash L is by definition A dash alpha dash L intersection Y. Right. So once I get this inclusion, I will get this inclusion again. Every time we are using this property, this idea basically, right? So we started with open cover of Y by C alphas, C alpha dash, and which are open in Y, and then we have finally shown that this open cover of subsets open in Y has a finite subcover. So this will prove that Y is a compact space. So therefore, finally, Y is a compact subspace of Y, subspace of X. So this is a simple criteria which we have proved regarding the compact subspaces. Let us go through the statement again. So what it says is that if I have a subspace Y of X, and I want to prove that that subspace is compact with respect to the subspace topology, then it is enough to show that if I have any open cover A alpha of the sets which are open in X and which covers Y, then this open cover A alpha has a finite subcover. So this condition we can also name, let us say by property star or whatever. So in property star, the difference is that we are taking the cover which are open sets in the X, not in the open sets in the Y, right? So only difference is that. So let us apply uh, this lemma, and get some more results. So the first application is that we can actually show that every closed subset of a compact space is compact. So if you remember the real analysis, then what are the compact subsets of R? So the compact subsets of R are closed and bounded sets. So for example, the closed interval is a compact space because it is a closed interval is closed set as well as it is a bounded set. So what this theorem particularly says that is that if I take closed subset of a compact space, so for example, if I take closed subset of the closed and bounded subset of the real line, then that closed set is always a compact space. Why? Because I'm taking closed subset of closed and bounded set. So closed subset of closed set is always closed, and since it is subset of a bounded set, it is also bounded. So this theorem holds trivially by that property that every compact subset of real line is closed bounded. So that will give proof of this theorem in the real analysis case, but we want to prove it for the general topological space, and therefore we will require the previous lemma, which has that star property holds, so that we can use here. So what we want to show that we have to take a closed subset of a topological space X. So let us say capital Y is a closed subset of a topological space X, and what we want to prove is our claim is that this closed subset Y is a compact space. So we want to show that Y is compact, right? And to show a so Y is closed subset, but Y is compact means we have to show with respect to the with respect to the subspace topology. And what is the previous lemma? Previous lemma says that Y is compact with respect to the subspace topology if and only if star property is verified. Star property holds, right? So what is star property? That if I take any open cover of Y uh, which has the elements of that open cover are open in X, then I can find a finite subcover. So if I can prove that property star satisfied by this particular Y, then Y is a compact by the lemma, right? Because lemma is if and only if condition. Star holds if and only if Y is compact. So let us start with the any open cover of Y where the sets are open in X. So we want to basically check the property star holds. So A alpha is a open cover of Y where A alpha is a open subset of X. Then basically we want to find a finite subcover of A alpha which covers Y. Then the property star holds. So first of all, what is given is that A alpha is a cover of Y. That means this property, right? For subspace, we take include the subset here. If Y is a topological space, we take equality. So this says that Y is covered by A alpha, where A alpha is open in X. Then using this cover of Y alpha, can I find a cover of X? So we know that X is a topological space, and I have a subset Y. If, for example, suppose Y is covered by A1 and A2, right? So what will be the cover of X? So we know that X we can write as a Y union X minus Y, right? And if Y is covered by A1 union Y is covered by A1 and A2, then A1 union A2 union X minus Y will cover X, right? So this is a particular case when Y is covered by two elements, but in general Y is covered by any arbitrary union, any arbitrary collection alpha. So what we found is X is covered by this set, and these sets are actually subsets of X, A alpha and X minus Y. So finally what we get is X is exactly union alpha A alpha union X minus Y. So these sets A alpha union X minus Y, that will cover the entire space X. And what we know in the hypothesis is that X is the compact space. So whenever I have a open cover, X minus Y is open because Y is closed. So X minus Y is open because Y is closed. So this is used here, that all these are open sets and this is also open set. So this is a open cover of X, and X is compact. So every open cover has a finite subcover by the definition of compact space. So that finite subcover, which is a sub collection of A alpha, I am calling it C alpha. Actually, I should write C alpha J because it is a finite subcover. So this cover C alpha J will cover X. it will cover the space X. So now this C alpha is a sub-collection of A alpha union the set X minus Y. So that means one of the C alpha can be X minus Y, or none of the C alpha equals X minus Y. So there are two possibilities. So if X minus Y is sum of the C alpha, that is the first possibility. So in that case, Y will be covered by all the C alpha other than this particular C alpha, right? Because we don't need X minus Y, because X minus Y does not intersect Y. So this is first case. And on the other hand, the other possibility is none of the C alpha is X minus Y. So none of the C alpha is X minus Y, then we can take Y is covered by union C alpha J running from 1 to n. Right. So in any case, in both the case, we will get a subcover of Y. Right. And this subcover of Y is a subcover of A alpha. So therefore Y is a compact space. So basically we are using the previous lemma that property star holds. So every open cover of Y by the open subsets of X has a finite subcover, that we have proved now. So therefore we can use the lemma. So what we proved is that, let us go back again to the statement. We proved that every closed subset of a compact topological space is compact in the subspace topology. Right. So so there is another result which is relevant, which says that if I have a, so in the previous result we have seen that if I take a closed subset of a compact space, it is compact. So that will give a information that when a closed set will become compact. Now converse question is when a compact space becomes a closed set. So this result is in that direction. So every compact subset of a Hausdorff space is closed. So let us recall what is the definition of Hausdorff space. So if you recall Hausdorff space, then the topological space X is Hausdorff if in which I take two elements x1 and x2, then I can always find two open sets u and v such that u and v are disjoint, and the first element is contained in the first set u, and the second element is contained in the second open set. So if for every x1 and x2 belongs to X, I can find for every pair x1 and x2, I can find pair of open sets which are disjoint and which covers the corresponding elements. Then such a topological space X we call a Hausdorff space. So we discussed that earlier, the details of the Hausdorff space. Here we want to prove that the compact subset of Hausdorff space is always closed. So let us try to prove this result. That so let us start with a compact subset of the Hausdorff space X, and we want to show that Y is closed, right? So that is what we want to prove here. And we know that if I want to show that some particular set is closed, what I need to show is its complement is open. So to prove that capital Y is closed, we will show that x minus y is open. X minus y, which is a complement of y in x, that is open. That is open set. So this set we want to show open in x. So what we will do is we know that if we can uh, if we start with any set we want to prove open, then we start with some element in that set, and we can show there is a open set or basis element which contains x naught, and it is contained in x minus y, right? So, so let us start with some element in x minus y, and so this is my set x, this is my set y which is closed, and I'm taking an element in x naught in x minus y, right? So x naught belongs to x, but it is not belongs to y. So what I will do is since capital X is housed off, and if I take any element y belongs to y, then y and x naught both are elements of x. So I can always find the neighborhood, two neighborhood which are disjoint, and one of them contains y and other contains x naught, right? So basically we can get this property because x is housed off. So for each element y in capital Y, since x is housed off, we get two disjoint open sets. These disjoint open sets u and v, that I can name them u and v, or I can name that in any way which I like. So basically this open sets actually depends on the point y which we are choosing. So therefore I will call this open set uy and vy, right? You can also call u and v, but because it depends on the point y, we will call it uy and vy. So the first open set contains x naught, the other open set contains y, right? So this open set contains x naught, so we could have called it ux naught, but we are calling it uy itself, right? Because this choice of u depends on basically on y, so therefore we are denoting it by uy. So this is exactly what this house of condition will give, and so what we got is every y is belongs to vy, so therefore singleton y is a subset of vy for every y, and we know that capital Y is a union of singleton y, right? Every set is union of singleton elements, and therefore and then we know singleton y is subset of vy, so we can use that here. So this is a subset of this set, so y is a subset of union of vy, and each vy is open in x, so therefore we got a cover of y by open sets in x. So that means we are in the situation of property star. Alright, so basically we will use the lemma here again, once again. So using lemma, now what we know is we know that y is compact, right? So we can apply the lemma, and that lemma will give the property star holds. So therefore every open cover has a finite subcover. So in particular this open cover has a finite subcover. So that finite subcover will denote by Vyj. So that is a finite subcover we are getting Vyj. Each of them, the elements Vyj's are open in X, open subsets of X. So now Once we got this collection V by J, which covers the space Y, what is our goal? Our goal is not to get a subcover. Our goal is to prove that X minus Y is open set. Alright, so basically I want to find the neighborhood of X naught. So to get a neighborhood of X naught, what I will do is we got this finite collection of V's, but on the other hand, I am also getting the elements uy1, uy2, uyn, right, corresponding to each vyj. So those elements I will take intersection of those elements, and that intersection I will call u. So if we call this intersection u, then since each uy j is open in x, this intersection is also open in x, right? So it is element of the topology on x. So u is open set. So I want to show that u is a subset of x minus y, and therefore we need to show that y intersection u is a null set. So therefore I am considering y intersection u, and y intersection u is this set. So that I will substitute here, and then I will use the property of union and intersection. We know that y is subset of this set. So therefore we get this is a subset of these, right? And that is a null set. Why this is a null set? Because y vy and uj, vy and uy are disjoint for every y, right? So in particular vyj and uyj, the intersection is null set. So therefore the intersection of these two set is a null set, and y intersection u is a subset of null set now, and therefore u is contained in x minus y. So we got that u is now we know that u is open set, and it is a subset of x minus y, and x naught belongs to u, because x naught belongs to each uy. So x naught belongs to the intersection of uyj, and therefore x naught belongs to u. U is a subset of x minus y. U is open set. So we know this property from the real analysis, that if I have a set in which if I take any element, and around that element I have an open set which is contained in that set, then that given set is always open. So that is what we verified here, that x minus y, if I take any element x naught belongs to x minus y, I can always find open set which contains x naught, and it is a subset of x minus y. So therefore x minus y is open set, and finally I will get y is a closed set, right? So let us summarize the result. What is the result? Result says that compact subset of the Hausdorff space is always closed. So we already know that the examples of Hausdorff space are real line R2, right? So in which this result holds that if we take any compact subset of R2, then it is always closed. So in particular, if I take closed and because in Rn, what are the compact sets? They are closed and bounded sets. So last result which I would like to discuss today is regarding the compactness is the topological property. So topological property means it is preserved under homomorphism or continuous function. So what is the statement? Statement is that the image of a compact space under a continuous function is always a compact set. So in mathematically what this statement means is that if I have a continuous function f from x to y, x and y are topological spaces, and y is not necessarily subspace, it is another topological space other than x. And if I assume the domain space capital X is compact, then the image is compact. That means image is f of capital X, and the image is compact. So what is the topology on image? Because image is a subset of codomain Y. So fx is compact with respect to the subspace topology on fx as a subset of Y. So in that particular topology, we want to show that this f of x is compact. Let us start with what we'll do is we will start with the open cover of the entire space Y, and then we will show it as a subcover. So basically, we are verifying the property Y, property star. So fx is contained in union alpha A alpha, where A alpha is open in Y is the codomain of F. Then if fx has if range has opens cover, then I can apply f inverse both the side. What I will get is f inverse of fx is subset of f inverse of union A alpha, and then we know f inverse satisfies this property that these two are same sets, and therefore what we get is, and this is basically x, right? So what we get is x is um, x is a subset of these. So therefore what we get is x is subset of this set. X is a subset of this set, and we know that converge is anyway true, that union is always subset of x, because f inverse A alpha is a subset of x, right? So basically here we have equality. So since f is continuous, and what can we say about these sets? So we know that A alpha is open in Y and f is continuous. So by the definition of continuous function, inverse image of open set is open. So therefore f inverse A alpha is open subset of X, and union of these sets covers X. So therefore this is the open cover of fx, open cover of X. This is an open cover of X, and what we know that X is a compact space. So since X is a compact space, we will get a finite subcover. Let us say this one, and once we get finite subcover of X, the corresponding subcover A alpha 1, A alpha 2, A alpha n, we will consider. Then we can easily observe that using set theory that it will cover f of x. So f of x is covered by a subcover of which contains open subsets of y. So therefore fx satisfies the property star, and therefore it is a compact subspace of y. Subspace of y. So here we can write that property star is satisfied. So basically we are applying the lemma. So I think this will be enough for today lecture.